Thank you very much. Thank you very much for this opportunity to be here and speak today. Let me just get the clicker so I can use the slides. All right, so we are all here, obviously, on a race towards what we call quantum advantage, right? Quantum advantage means running useful quantum algorithms on actual quantum computers. In other terms, running quantum algorithms on quantum computers faster than they could run on their classical counterparts, right? And in order to win this race, there are actually two ways to get there, right? So one of them is what we call the fault-tolerant quantum computation, and the other is the NISQ quantum computation. While I'm a big believer in NISQ, I believe this can happen. It will take a little bit more time, but it can happen. Today, I will focus on fault-tolerant quantum computers, which is the sure way to get there, right? So fault-tolerant quantum computers, in other terms, super polynomial advantage, will require something like 1,000 qubits. Okay, that sounds quite easy, right? So maybe we can do it tomorrow, right? But on the other hand, it will require 1,000 qubits with extremely low error rates. Right? So it is impractical with anything that we have today, because today we're still at a very, very, very low fidelity regime relative to that. Of course, I cannot generalize all types of qubits with just one number. We have ions, we have atoms, we have superconducting qubits, and so on and so forth. But generally speaking, we're still far away from what we actually need. Okay, so there are two ways to bridge this huge gap. Right? One is just to keep on working hard until we get there. Right? This will probably take us ages, impractical. The other way is trying to use error correction, right? The other way is trying to use error correction, and this is going to be my focus here today, right? So quantum machines, just a few words about the company. So we're over 160 people now employed in 12 countries. So we're one of the biggest companies in the field globally. We've raised over $130 million from VC funds and government funds. So we're one of the most well-funded companies in the field globally. We've recently established the Israeli Quantum Computing Center, a cutting-edge quantum center that's based in Israel. We have an M&A strategy. We already acquired one company called QDevil in Denmark, and we're lucky to have many, many customers all over the world, over 300 customers now globally, and keep on growing. Now, the focus of my talk is not going to be on all of our products. Of course, we have many, many products, including both room temperature control and cryogenic elements for superconducting and spin qubits. But it's going to be mostly on the OPX1000, which is our flagship product. Okay, so the OPX1000 is trusted by the builders of some of the world's largest and most advanced quantum computers, and there's actually a lot that we baked into it. So the first is around scalability, unrivaled scalability. This packs up to 80 analog channels in a 3U module, so this is an extremely high channel density that can take you very, very far. It's also scalable in terms of the co-working with GPUs in our collaboration with NVIDIA. I'm going to talk about this a little bit today. In terms of analog specifications, so we have used the most advanced analog components that you can find globally now, direct digital synthesis. So there are no mixers, no double heterodyne schemes, no RF SOCs, which combine both analog and digital in the same chips. So this is what really allows you to get the most pure and the best SFDR one could aim for. The third component is processor-based controllers. So we have put a lot of emphasis into packing classical computation into our system. So very, very advanced classical computation that allows unmatched compute power and unmatched feedback latencies. The third is ease of use. The system is modular. You can mix and match different quantities of channels and can help you scale up with great ease in terms of the programming. Going from 1 to 1,000 qubits is far easier than one may think. And the question, and of course, our collaboration with NVIDIA that I'm going to talk about. And the question is why, right? So why did we put so much effort and so much investment into developing a control hardware for quantum computers? And in order to answer that, I will try to use a single example. Okay, the example of factorizing 21 with quantum error correction. Okay, so in order to do that, of course, I need to get concrete because otherwise it's going to be too broad, too theoretical. And I'm going to use a simple example using 5 computational superconducting qubits, surface code with distance 5. Okay, these are some choices that we have made. And from that, we're going to try and deduce some of the requirements that went into the design of the controller. Okay, so let's start breaking this down. So first of all, this is the circuit. It looks pretty easy, pretty naive. Actually, it has only 5 qubits, 4 2-qubit Cliffords, and so on and so forth. But as I said, I'm going to use surface code. So that means that some of these gates have to be made surface code compatible. Not all gates that we have here are surface code compatible. This already makes it a little bit more of a mess. Right? But then if we look at it more deeply when we implement this with surfaces, then sometimes we may take something that is just a 2-qubit gate like this C0, but then we need additional surfaces. Right? In order to implement this 2-qubit gate, what I actually need is 3 surfaces and implement gates between them, as you can see right here at the bottom. What I'm trying to say here is that you can break down all of these into far more complex surface level circuits, and some of the details that you see here is actually very, very challenging to implement, and I'm going to elaborate about that in a few moments. So if you look at all the details together, it becomes already quite a complex circuit here with 18 surfaces and 300 fault-tolerant gates, as well as specifically 13 decoding-based feed-forward operations. So we already have quite a lot of feed-forward-based operations that will be quite a serious burden for the control electronics to implement. Then, of course, there is the last stage, which is the physical stage, because if we take each surface here, we need to break it down into the different physical gates. Right? So what you see here, every box here, the blue box and the orange box, is basically a tick or a talk in the time of the error correction, and then it's implemented with many, many physical gates. And overall, we have here slightly over 1,000 qubits, physical qubits, to operate. Something that started with something as naive as just a 5-qubit algorithm. So all in all, we have quite a bit to do here. And what you will see is that there is quite a lot of color coding here. It will be related to the requirements that we actually have. So let's have a look. From analog specifications, you see, in order to make that happen with 96% success rate, we need the single gate error to be 0.1. Okay, this already imposes quite some stringent requirements like ultra high gate fidelity and extreme phase stability. That's not very easy to implement, and I will talk about how we did that at Quantum Machines. Implementing the fault-tolerant gates requires a lot of processing. Okay, because these are gates that are not just sending pulses. Each one of them requires processing. Okay, we have the magic state preparations, 13 decoding-based feed-forwards. All of this requires a lot of processing, real-time feed-forward, non-deterministic protocols, real-time decoding of thousands of bits, and so on and so forth. The third component is scalability. Again, we started with just 5 logical qubits, but already that demands high scale. In this case, we have 1,015 qubits, and this already requires a lot of channels to be operated all together. But the additional note that I would like to make here is that if we look at the analog specifications, it is one thing to implement it for 1 or 5 or even 50 channels. It's a completely different thing to do it for such a large scale of channels and of qubits. Okay, so the extreme phase stability has to be looked at scale. And the last but not least is ease of use. Okay, in order to actually realize that, you can actually set up a 1,000 qubit control system, but maybe it will not work for a long, long time. In order to actually make good use of it, you need extreme ease of use, and you also need a lot of flexibility, because what you see here in red are actually choices that we have made in this analysis. Okay, this analysis, namely this modeling that we have done, we could have chosen different numbers. It would have resulted in different things, and therefore you need flexibility so that every time you can implement something else. So this is the main thing that I want you to keep in mind, and I'll try to give you just a small glimpse into that. So in terms of scale, the OPX1000 can be scaled up to a very large number, 26.7 channels per U. It's a massive density. And it can also be scaled up to a basically arbitrarily large number of modules. We have our QSync technology that allows you to go very far and down to 100 nanoseconds of communication between two modules. Okay, it's to the extent of my knowledge, it is the lowest latency in the market, and therefore allowing you to scale up very substantially. We've already demonstrated quite a few deployments with large quantities of systems. So, for example, this is from Alice and Bob, a dear customer of ours in France. This is what we have deployed recently in Israel, in the Israeli Quantum Computing Center, with the help of a fellow Korean that has been part of this operation, and it's still making incredible progress. Now, I want to look at, for a moment, at phase stability, which I mentioned earlier. You see, if you want to run now a quantum sequence, you need some pulses to run for quite some time. But these pulses will be distorted in the course of time. Things will change, right? Now, this change can be decomposed into two main things. One of them is a drift, which is the main line that you see over there, and the other is the noise, right, which is kind of the fluctuation around this main line. At Quantum Machines, we worked really hard to analyze this and take care of it. Okay, so first we set the goal, which is an I-swap gate error with less than 10 to the -4, a very stringent goal, because we needed to make sure that whatever we do can actually address that. Okay, so the analysis, this is some of it is actually very known. This is how the phase difference between the channels of a 2-qubit gate, a 2-qubit I-swap gate with a coupler, will actually influence and deteriorate the gate over time. Okay, and you see that the more the phases drift, the bigger the error is. And it's quite susceptible to that. But the thing is that it's not just between two neighboring qubits, because one is coupled to 2, but then 2 to 3, 3 to 4, 4 to 5. You actually need to take care of the phase stability across the entire cluster. Okay? So this is the analysis that we've made, and we've defined exactly what is the threshold that you would need and how you can get there. So the OPX1000 takes care of it in many different ways. One is, of course, just the analog performance itself. So, for example, phase noise less than 5 millirad RMS jitter, and the phase drift less than 6 millirad in 1 hour. So these are outstanding results that would allow you to actually get the result that you want. You see here the fidelity of the I-swap that we're seeking to get here. So we can remain below the threshold. But this is not enough, okay? Because actually there is much more to be done. And one of the things that we do at Quantum Machines is we use processing, real-time processing, to do better than that. Okay, so what we can do is we can actively make sure that any time that you're approaching the threshold, you can pull back the different parameters using real-time feedback. And this is what's implemented in the OPX1000 in its digital capabilities. So again, as I said, no mixers, no double heterodi, no RF sock, also no phase drifting PLLs, which could cause quite a lot of trouble for many types of qubits. But then, of course, the processing itself, and here we have a beautiful result from Seoul National University, from Do-Han Kim's lab, where they implemented Bayesian estimation-based tracking and correction of a qubit frequency in real time. Okay, all of that done in real time. It was recently put on archive. Very beautiful result. Also, beautiful result from SKKU with fast and precise cross-resonance calibration. Results that we're very proud of and are happy to show here. So I want to take you back to the real-time processing, and specifically on error correction, because I put it aside for a few slides. If you look just carefully for a moment, you see I overlaid a few colors here. These colors are actually the decoding tasks, the decoding activities that you need to perform during the circuit, while the circuit is running. So if you look at these tasks, there are also dependencies between them. So not only you need to do processing, but you need to feed forward the processing result in the course of the circuit. Now, in addition to that, we have the T gates, which are required in order to implement the magic states. And there are actually many ways to implement these T-gates on these systems. We find that the most efficient way to implement that actually uses advanced real-time control flow, specifically repeat until success circuits that actually require real-time processing and can take you from a fidelity of 98 to 99.7 in these specific systems. So already, if you look at the basic operation to apply all these tens of thousands of measurements and even more gates, you need processing. You need to generate all of these pulses. For that, you need a lot of processing power. But then, as I mentioned, you need to add on top of that, you need to add all of the decoding. Now, the decoding is necessary both for the gates themselves, because once you're in the surface code, for every gate, you have some processing to be done, but also for the feed forward, because sometimes it is necessary. You cannot delay all of the feedback to the end of the algorithm. Sometimes you have to implement that, like in the, such as the case here, which is the magic state distillation. To address that, we have our collaboration with NVIDIA. We are promoting the DGX Quantum, which combines the OPX and the Grace Hopper by NVIDIA. You can have a look at this paper that we co-published with NVIDIA recently. So the controller is talking directly to the qubits, and the controller on the other side is talking to the Grace Hopper, to the GPUs, in order to take care of the error correction and the decoding. So we separate this into, again, this segment, so real-time and non-real-time for the decoding. And I want to give a couple of examples here. One beautiful example is from Dirac. Andrew Zurek was here yesterday to give a talk. They actually implemented a real-time sequence in order to better stabilize their two-dot state. So this is something that requires advanced real-time capabilities. They learn the state in real time, and based on it, they actually are able to, with a better fidelity, to cool down their qubits into the ground state. And then, again, for the decoder itself, we find that you need a round trip to be less than 10 microseconds in order to implement that well. And with NVIDIA, we are already implementing the interface that will have less than 4 microseconds, and therefore would allow to implement even large-scale error correction codes. So, lastly, I want to talk a little bit about ease of use to emphasize how important that is. And it is especially important because we're still in the early days of quantum, right? And the thing is that every month, every week, every year, we come up with completely new ideas. So maybe a completely new error source, we come up with it, and then we need a new syndrome in order detection in order to actually see it. We need to implement a decoder that will correct for these errors, and then we are completely changing the scheme in order to address that. There are different ways to go about this. One of them is actually to re-implement FPGA code, but this will take a very long time. Okay, and if you're spending months on every cycle, you might not ever converge on a useful quantum computer. What we're proposing here is a paradigm where you can easily implement new decoding schemes employing both QA, a pulse level language, and NVIDIA CUDA on the decoding level. I want to give an example by another speaker that spoke here yesterday. That's Ferdinand Quemet from the Niels Bohr Institute. So over there, they have implemented an extremely advanced real-time processing scheme where they implemented a Bayesian estimation of a parameter of the Overhauser gradient in the, which is a field in the vicinity of the qubit. Okay? Now, implementing a probability distribution and re-estimating it shot to shot is an extremely hard task, and they could have done it just by very simple coding. Okay? Because QA allows you access to the lowest level one could ask for, and it's extremely easy to use. And the reason I'm giving it here is because we may, as a community, every week, every month, or every year, come up with a completely new idea or paradigm for error correction, error mitigation, and so on and so forth. And you need a system which makes it extremely easy to implement those. So, wrapping up, I hope you're now understanding why we put so much effort and so much resources into developing such an advanced control system that's capable of, by the way, not controlling only superconducting qubits, but also ions and atoms and defect centers and photonics. We can make use of it. And if you want to have a look, we can actually factor the number 21. I hope you're ready. Hang on tight, it's happening. So this is actually a real simulation, an extensive simulation, a comprehensive simulation that we have done. This is not just kind of, well, you see, it's actually working. We have done the simulation end to end. This also appears in the paper that we have published with NVIDIA recently. We are happy to share the information with anyone who wants to see. So you can drop by our booth. We have a very, very nice demo that we will show you. Thank you very much for your attention.
네, 자, 이제 질문 받도록 하겠습니다. 질문 있으신 분 질문 주십시오.
Thank you for the presentation, and I want to know. But it is. I know that it is a very difficult question, but I need this kind of comments from you. Is that do you think which top? I want you to rank 1, 2, 3. Which platform is at this moment number 1, number 2, and number 3? Your personal opinion, I want to get.
It is a very hard question, not just technically, but also politically. I admit that just in this room right now, there are customers of ours working on atoms and superconducting qubits and spin qubits and others. Some of them I quoted today, so I will not be able to comment on that. Some of them might like my answer, the others will not. So if that's okay, maybe we can discuss this privately afterwards.
Thank you for a great presentation. Regarding on QEC, there is a various device architecture and various codes here, and it's still developments on many researchers. I'm curious about what is the good combination of the code and device architecture, and for instance, IBM heavy square and heavy hexagon and so on. Yeah, and what's your opinion on that?
Also a very, very hard question. So first of all, humbly, I admit that I'm not the biggest quantum error correction expert on the planet. So there are many, many schemes. I think that one of the leading ones, I will not be telling a secret here, is surface code. And I think it's pretty suitable for many types of architectures, some better, some worse. But generally speaking, it's very common to believe that this will be the way forward. Other than that, I'm happy to discuss in private more extensively. But the idea, I want to go back to the idea that I was mentioning earlier, which is that error correction codes may change over time. Okay, so what we think today is a good code may completely change in a couple of years' time, and this is why we need, again, the flexibility and the ease of use of the system so that we can iterate quite easily, so that, again, eventually we converge on a useful quantum computer. Because if every iteration that we want to make of a code or of a device will take too long, then we might not converge ever, right? So the ease of use and the speed of progress are of utmost importance and a major focus for us at Quantum Machines.
네, 여러분 큰 박수 부탁드리겠습니다.